Welcome class to chapter 14 in AP Stats. And welcome to our guest cameraman in the back there. Hey Parsa, thanks a lot. Parsa, why don't you kind of move forward so everybody can get a little bit better view. I promise we'll keep our social distancing. We'll all be good. All right, so here we go, chapter 14. More inference, of course. That's what second semester is all about. Chapter 14 is doing inference on regression. So we're going to kind of be taking chapter 3 and 4 and blending it with second semester inference. Okay. So again, we need an explanatory response relationship to do regression. We have an explanatory variable x, response variable y. We're going to do confidence intervals about the slope of our regression equation, and we'll also learn to do a significance test. Okay, so when we do regression, right, we label it our regression equation with a y hat, and we have a intercept and a slope. But realize that's a statistic. That's not a parameter, right? That's coming from sample data. So this regression equation is a statistic that is estimating the true unknown equation. So that's why this is mu sub y. And instead of A, we're going to use alpha, and instead of B, we're going to use beta. Again, the calculator can switch those around. Just realize there's a true slope and there's a true y-intercept, but they're unknown.
LeBron James!
Parsa, calm down. I know you're missing your basketball season, but sheesh. All right. So the idea here is that with repeated data sampling, right, the samples should have variation. For every x value, you should have a variety of responses that you would observe if you sample repeatedly. So we want each x value to show that variation, and that variation should be normally distributed. We'll talk more about that in a minute. All right, again, it's a statistic. We don't have the parameter, so we're going to use S, and here's how we calculate the standard error. Right? Observed y minus predicted y squared divided by the degree of freedom of n minus 2. And then we square root that. You can see degree of freedom is now n minus 2 because we have two variables, x and y. And of course it takes, if you only have 2 points, you're not going to have any variation about the line, right? You get 0 variation, and so you have to have a minimum of 3 points in order to show any variation. And of course, the variance would be s squared, and hopefully you guys remember how to do residuals. It's the observed y minus the predicted y, that's also known as the residual. Okay, here's how we do a confidence interval for the slope of the line. The statistic that we got from our slope, plus or minus, is the critical t, so we're going back to t, multiplied by the standard error of the slope. And here's how we calculate the standard error of the slope. Let me grab a formula sheet, see what it looks like on this year's formula sheets. Okay, and here it is. It's the very bottom section on that back page for the slope B and all of the formulas that you need. Okay, so it shows this formula right here. And again, I'm reminding you, this is a t distribution, so we have n minus 2 degrees of freedom. All right, so your hypotheses. The null hypothesis will always be the true slope is 0. If the true slope is 0, that means as x is changing, y isn't changing in anything other than a random chance. So in other words, that's saying they're not related. There's nothing here, null hypothesis. Alternative could be one-sided, or it could simply be, hey, I think there is an association, but I'm not going to say direction. To get your test statistic, you'll do B divided by the standard error of B. Now, the calculator typically gives you that, but the calculator doesn't give you standard error of B. So we normally actually end up solving this formula for the standard error of B. And the calculator gives you both T and B. So you just say B divided by T. There's your standard error of B. Okay, so here's the steps. You're going to enter the data in your calculator. You're going to make a scatter plot. Remember, we need to see a linear association. Calculate your least square regression line. This is what everybody keeps forgetting to do on their special problems. You have to make a residual plot, because if your residual plot is curved, the data is not linear, and we shouldn't be using linear to estimate it. Now here's the new piece. This is the inference piece. So instead of just doing a linear regression, you now have in your test menu the linear regression t-test as a choice. Okay, here are the conditions or the requirements, what makes your calculations valid. You need a simple random sample, or in other words, good, unbiased, randomly collected data. I mentioned this earlier. For any fixed value of x, you need to be observing responses that are varying normally. And of course, you need independence from one observation to the next. Okay. We need a straight line relationship. We're doing linear regression today, so your residual plot needs to be nice random scatter. And there you go. And lastly, we need a consistent standard deviation of y. In other words, a residual plot that doesn't show fanning. Hopefully you remember when we talked about that back in chapters 3 and 4. So if I'm seeing fanning, then my standard deviation is changing as x changes. The standard deviation of y is changing as x changes. All right, so let's try a problem. Step 1, enter the data in your calculator. Make a scatter plot. Look for any outliers, look for any influential points. Okay, we're going to do a linear regression. Then we're going to do our significance test. Okay. So, again, feel free to pause the video, or you could just have the PowerPoint pulled up on a separate window, and you could enter the data in your calculator now. So here's my data. And of course, this is matched paired data, right? List 1 is the golfer's first round score, and then list 2 is that same golfer's second round score. So we're seeing, is there a relationship? All right, so step 1, we're going to make a scatter plot. And there we go, there's our scatter plot. Not a whole lot of points. This point here is a little bit concerning, potential outlier, but let's continue. It doesn't look curved at least. So let's do a linear regression. And again, we've been calling B the slope, so I'm gonna choose that one just so we don't get confused. So list 1, list 2, and we're gonna store that equation. Hopefully you remember that command. And there you go. Let's write that down. And let's put our correlation down while we're at it. And just a quick review, hopefully you guys remember, that's the coefficient of determination. So we're saying roughly 47% of the change in y, or in other words, round 2 golf scores could be predicted by change in x, or the golfer's first round score.
LeBron James.
Parse that. All right, let's move on. Next, we need to get those residuals. Look at a residual plot. So go into an open list. You can use the resid command, or you can remember it's simply the observed y minus the predicted y. Remember that is, where it is, right there, functional notation. So we're telling the calculator to plug in the list 1 value into the equation that we've stored. There's our residuals. And now residual plot. List 1 is still x, but now list 3 is the y. That's the residual. Okay, so here's our residual plot. Again, not a lot of points, but it's clearly not curved. I am a little concerned, again, these last 2 points do show a bit of fanning, much larger residuals, which actually isn't surprising. These are golfer scores. Very good golfers are going to be quite consistent. Over here, these would be poor golfers. They're going to have a lot of variation in their scores. So really, we're probably failing that check of a consistent standard deviation of y. But we'll proceed with caution. Okay, so now we will go stat, test, and towards the bottom, there it is, linear regression t-test. Okay. Data's in list 1 and list 2. Just leave frequency as 1. Let's do a 2-sided test. Leave regression equation blank. The calculator will calculate it for you and calculate. So there's your t, your p-value, your degree of freedom, and if you scroll down, there's your slope. That's the standard error, but that's not standard error of the slope. That's the standard error of the line. Okay. So let's write all this down real quick. We already have the equation there. So we have a t of 2.99. P-value, 2-sided p-value, approximately 0.01. Degree of freedom is 10 because we had 12 ordered pairs of data. Probably should have wrote down our hypothesis, right? True slope is 0, meaning the round 1 and round 2 scores are completely unrelated, which really doesn't make sense. Alternative hypothesis would be there is a relationship. The round 1 and round 2 scores are related in some way. We have to talk about our requirements. SRS, we're unsure, right? So you've written this sentence about 1,000,000 times. Okay. Is the true relationship? Yes, it looked reasonably linear from our residual plot. There was nothing on our residual plot to cause concern with that check. So residual plot. Showed random scatter. Linear regression would be appropriate. Okay, now, are the y values responding normally to each x value. Here's how you check that. Look at a normal probability plot of your residuals. So I'll just kind of put that over here. Normal probability plot of the residuals. Right. So in other words, we should be seeing a lot of residuals that are close to the line, small magnitude, and fewer of large magnitude because they should be responding normally. So let's do a normal probability plot of those residuals. Okay, so normal probability plot's that one. Residuals will list 3. And there we go. The residuals are looking like they're pretty normally distributed because your normal probability plot is fairly linear. So I'm going to say we pass that check. Normally have 1 L, 2 L's. Okay, so we passed that requirement. All right, so now looking at our p-value, you can see we have strong evidence to reject our null hypothesis. So we're going to conclude that yes, there is a relationship between the round 1 scores and the round 2 scores. Okay. And hopefully I have that written in the PowerPoint so I don't have to write it on the board here. Yay, yay. Okay, so that's what we calculated. Oh, here's calculating by hand, right, using the formula on our formula sheet. So you can do that by hand, or as I mentioned, the quick and easy way to find the standard error of B is to simply take our B. So we can just use our B and our T to get that same value much easier, right? So 0.69 divided by 2.99, and that would also give me the same value there. Okay. Now, to do our confidence interval, we're going to take our slope right there, 0.69, and then we're going to add or subtract our critical t with 10 degrees of freedom multiplied by that standard error of B that we found. Okay, so basically that's what you're going to be using. You're not going to have to do this by hand. It's way too much work to do it by hand. It's perfectly acceptable to do this using your calculator. So just report your T, report your B, and then divide B by T to get your standard error of B. That goes right here for your confidence interval. And hopefully you guys remember T star, right? Use your formula sheet. So 10 degrees of freedom. I think this was a 95? Yeah, 95%. So 10 degrees of freedom, 95%. There it is right there. 2.228. So that's where that number came from. And of course, that's the slope, the statistic for slope. Okay. And notice, 0 is not included in the interval, which should not be a surprise because our p-value was significant, which means we suspect there is a difference. Remember, if 0 is inside of that interval, then you'd say, oh, it looks like there isn't a difference. Okay, last thing. since we're not doing these calculations by hand, and it's perfectly acceptable to use a calculator on all these problems and just report what you found, you might come across problems where you've been just handed a computer printout and it's your job to interpret it rather than have to enter all of that data in your calculator, which is time consuming. So oftentimes this is what you'll get is what's called a Minitab printout. Your Minitab printout, get this out of the way. We'll start by identifying the dependent variable. So in other words, the y variable was 2. So for us, that was the golfer's round 2 score. It usually reports, or always reports, r squared, or in other words, your coefficient of determination. Notice, okay, what I've put in bold here, this will not appear on the printout, but I'm pointing out there's no r value given. So you have to use your own brain and go, oh, if r squared is 0.47, right, square root that to get r. But realize r could be positive or negative. You have to use the context of the problem and the information given to figure out if r should be positive or negative. How do you do that? Well, look at the slope, right? Remember, if you have a positive slope, you'll have a positive r. If you have a negative slope, you'll have a negative r. So look at the slope of your equation, which is right there. And since I saw the slope is positive, when I square root the 0.47, I'll know to report a positive r. That's a common mistake on a chapter 14 test, to mess up the signs on your r. Okay, notice they report s. Okay, s is the standard error of the line. They'll tell you the degrees of freedom. Okay, then down here in the printout, this is going to give you your actual equation. So where you see the constant and you look at coefficient, that's your intercept, your y-intercept right there. Okay. We're not going to use these 3 values, so don't worry about that because we're not going to do any inference on the intercept. Okay. Down here where it says round 1, that's where you're going to find your slope. Okay. What's in red here is not on the printout. I put that in there just to help you understand it the first time you come across one of these printouts. So there's your slope. The computer printout's nice. It gives you the standard error of the slope, okay, which your calculator doesn't give you, right? We had to calculate that by doing b divided by t, but the computer printout gives you that. There's your t value, and there's your p value. The computer will always report a 2-sided p-value. So if you're doing a 1-sided test, divide that value by 2. That's another common mistake. We'll give a computer printout for some question and we'll signify a 1-sided alternative hypothesis, and students will forget to divide this one by 2. Yay, we're all done. Parsa, I want to thank you from the bottom of my heart. You were a fantastic cameraman today. Go Lakers.
LeBron James.